So hello everyone, very glad to have this opportunity to present our work in this special way. My name is Yang Yu, and I'm a PhD student with Professor Goyal being my advisor. We are currently working on the reconstruction of a quantum theory named quantum questions. So what is the motivation of this work? The main goal is to explore the essential properties of quantum theory. If not using linear space language, how can we catch the relations between quantum measurements? And information is the tool we are using. And the information approach to quantum theory is definitely not a new thing. There are many different styles. So here, I'd like to talk about several historical approaches on the same style which inspires us. Rowley introduces the idea of information in quantum theory. The basic unit is a binary outcome projection, which acts like binary question. The information of the system is a sum of selected questions, and there are upper bounds for both information of the binary projection and information of the system. However, this is a very raw structure. The structure of these finite questions is not clear. In the meantime, Bruckner and Zeilinger proposes a more detailed information approach to quantum theory. The paper I cited here is 2002, but in fact, they published several different papers in 1990s, almost at the same time with Rowley. But this one, I think, is an integration of their ideas. Again, there will be upper bounds of information. But the most important thing is that they provide a way of calculate the system's information based on complementary measurements. For a single qubit, these complementary measurements are just polymatrices. And one other important consequence is that the Shannon entropy cannot be used in this structure because it's not unitary invariant. Horn, as he introduces yesterday, initiates a full reconstruction of qubit quantum theory. So the system is determined by a subset of questions Qm, and each question is a binary projection. The structure of the subset is investigated and derived from informational postulates, including the upper bound and lower bound of the information. So moreover, the most important thing for us, we think is interesting is the logical gates, the representation of the joint measurements. And we will be generalizing this idea to higher dimensional cases. I will discuss it later. So in some sense, what we did is a generalization of these informational ideas to high order dimensional case. Most of the reconstructions are focusing on qubit quantum theory. And indeed, a measurement in high order dimension can be decomposed as summation of projectors, and each projector is binary outcome. But the overall structure will be different. And we will see that this generalization is non-trivial. The probabilities in our work are all written in terms of conditional probabilities, and the context is explicitly shown. In this way, the probability will be more messy, but will be more clear. Our information measure is also probability-based, but it's a weak measure. I will explain that later, but this weak measure can still yield useful results. And finally, we provide a one-to-one correspondence between our approach to regular quantum mechanics, so making the abstract formalism not so abstract. So before presenting the basic settings of our structure, we want to talk about some properties of qubit systems, because we want to mimic these features in qubit system and then generalize to high order dimensional case. So here is a picture of block sphere. The pure states of qubits are distributed on the sphere, and each point on the sphere will be an eigenstate of some projections. But noticing that in the center of the sphere is a very special state, which is a maximum mixed state. The outcome probabilities of any projections applied on this state will be just a 1/2. So this center state has no tendency. So we observe several different effects on the qubit systems. The first effect we observe is that from the viewpoint of state tomography, the state of a single qubit can be determined by outcomes probabilities of projections. So theoretically, we can choose 3 arbitrary different directions, but the most commonly used are 3 perpendicular directions, which are just the Pauli matrices. So in the density matrix, we can see that if the block vector is 0, so if this term is 0, the state will be just a 1/2 identity, and the 1/2 identity will be the center of the block sphere, V. The second fact is about two-body system. In the density matrix, we can see that there will be local measurement terms, these two. And for local measurement, the operations are performed on subsystems. And there will be also joint measurement terms. The joint measurements, which are operations performed on both subsystems. These joint measurements represent the correlations between subsystems, and noticing that both the local measurements and the joint measurements have the same outcomes, +1 or -1. So joint measurements are degenerate. The third fact is about the relations between these correlations. So these correlations are the terms in the 2-qubit density matrix, sigma I and sigma J are Pauli matrices. The commute is just means a commuting operator, and mutually unbiased I haven't introduced. Later, I will give you a formal definition of mutually unbiased, but here it's just like the relation between Pauli matrices, sigma X and sigma Y. Of course, we haven't introduced that information, and I'd like to illustrate the non-informative by 2 examples. So the first example is about commuting operators. Let's think about the 2 commute joint measurements, sigma X tensor sigma X and sigma Z tensor sigma Z. So their common eigenstates are just the Bell states. Okay. So assume we take measurement of sigma X tensor sigma X at some time moment T1. The post-measurement state will be projected into the eigen subspace of this operator. Based on this knowledge, how can we determine the outcome probability of another? The best we can say is that the outcome probability is unknown. So here, I will be the background knowledge of, which is actually which are the fundamental postulates of quantum mechanics. So this is a Bayesian convention. T2 will be some moment later than T1. And so the quoted term will be a proposition. This is what we mean by context dependent. So this means at time T1, we take measurement of this operator and obtain an outcome. We may see that our current knowledge is not enough for us to determine this outcome probability because It's really dependent on the initial state of the system. So what if we really want to assign some values to this thing, because we don't want to deal with unknown things? And here, I'd like to choose the initial state as this one, the very special one, the identity. So similar to the single qubit case, is the center of the sphere. This is the analogy of the center of the Bloch sphere for 2-qubit case. And this state has no tendency to any projections. Under this choice, we can see that the outcome probabilities of sigma z tensor sigma z will be just 1/2. And this means the measurement of sigma x tensor sigma x provides no information about the outcome of sigma z tensor sigma z. And if we swap the order of these two measurements, we will be arriving at the same result. This is what we mean by non-informative. And the second example is a mutually unbiased case. So these two operators are not commute. And we get the similar result, but this time it's a little bit special. We needn't to assume the initial state of the system. So this is the third fact about the relation between correlations. And the last fact we observe will be the relation between joint measurements and local measurements. So of course, the joint measurements can be regarded as a product of two local measurements. So in theoretically, implementation of this joint measurement can be regarded as two consecutive local measurements. But what we are more interested in is the probability of this joint measurement from the viewpoint of state tomography. So here I write the outcome probability of +1 of this joint outcome probability. So the outcome probability of getting -1 will be equal to the probability of getting different outcomes of two local measurements. So here you can see that the probability is very messy, and but this is what we mean by context dependent. And the time order here only shows that the two local measurements are performed separately on the same system. But and the equality holds for arbitrary time orderings. And we think the relations between those measurements, the relation between correlations, the relations between joint measurements and the local measurements are the most important features for qubit systems. And then we will take the abstraction of these observed facts. So noticing that all these measurements on qubits are binary outcome. And we may abstract each measurement as asking a binary outcome question to a black box. There will be numerous measurements that can be performed on qubits. So such a black box can be characterized as a collection of many binary questions labeled as Q. The state of the system is now equal to the outcome probabilities of these questions. And then we'd like to take the generalization from binary case to n-ary. Each question has the same outcome, ranging from 0 to n-1. So if reducing to the binary case, it's 0 and 1, not +1 and -1. We are taking the outcomes in this form just for the sake of calculation of convenience, because this set of numbers is just the finite field of order n. Each question has the following property, and this is the analogy of eigenstate of an operator. Assume we have asked the question and obtain an outcome Q. if we keep asking the same question to the same system, we will get the same result. Here, the H, this denotes to the history of the system. So this includes all the historical interrogations we have conducted on the system. And I, again, this is a background knowledge of the system, including all the assumptions we will introduce. And now we can introduce the relations between these questions as a mimic of quantum measurements. The first, this is the analogy of commuting operators, and we represent it in probabilistic form. Of course, it's not exactly the same as commuting operators, but very similar and enough for this work. And this is another relation. This is the analogy of mutually unbiased operator. Again, it is represented in terms of probabilistic form. And then we can introduce our basic assumptions. The first assumption is coming from the intuitive idea that although the system contains infinite many questions, the degree of freedom of the system may not be infinite. We assume that there is a subset of questions determines all the state of the whole system. The only restriction is that all questions in the subset are pairwise, non-informative. And later we will try to derive this structure of this subset. The second assumption is concerning about composite system combined by subsystems. And just recall that in the 2-qubit systems, there are local measurements and joint measurements. The correlation term is represented as logical gates. And the logical gates is a mimic of the relation between joint measurements and the local measurements. Moreover, the correlation term have the same number of outcomes. So their outcomes are ranging from 0 to n-1. This is an example of a two-body system. And in fact, we can generalize this form to many-body systems. But most of our calculations and derivations are based on one-body and two-body systems. We meet some calculation difficulties on many-body, arbitrary many-body cases. I will explain the difficulties later. The third assumption is about the restriction, a further restriction of the subset QM for 2-qubit case, two-body case. So this is an analogy of two-body qubit density matrix. And this assumption will be helping us to explore the structure of logical gates. So how many logical gates and what do they look like? Because the questions in this subset are pairwise non-informative, and this immediately provides us two restrictions of logic gates. So now we can try to explore the logic gates first. The first restriction is about the relation between composite question and the questions from subsystems. And the second restriction is about the relation between two different gates, if there are more than one gate. Okay. So as long as we call them logical gates, so we can represent them in terms of truth tables. And this will be more clear for us to see what is non-informative. So this is a binary case. There will be 16 truth tables for a binary case. So I only selected 4 of them. The AND gate didn't satisfy the first restriction, because if we know the outcome is 1, we immediately know that each of the subsystem question cannot be zero. So this means that the AND gate provides some information. They are not pairwise informative. The exclusive OR gate satisfies the first restriction, and we can see that this is just the analogy of tensor product. So if the two local measurements have the same outcome, the joint measurement has outcome 0. And in fact, we can see that XNOR gate also satisfies the first restriction, but they are not different. The XOR gate and XNOR gate are actually equivalent up to a negation. The binary case is simple. Since there are at most 16 tables, we can indeed check one by one. 16 is not very much. How about high order cases? This is an example of a ternary case, ternary multiplication, ternary addition, and ternary subtraction. So we can see that ternary multiplication is not valid because once we know that this comes to the question outcome is non-zero, we immediately know that QA and QB are also non-zero. So this provides little information. They're not pairwise, not informative. The addition and the subtractions are pairwise, non-informative. They satisfy both restrictions. So we can check this by one. Assume we have a ternary addition of an outcome 0. Okay, we immediately have 3 choices: 0, 0, 1, 2, and 2, 1. And this corresponding to 3 different possible outcomes of a subtraction, which means the addition and the subtractions are non-informative. Each of them provides no information about the other outcome. Okay, so we now know that in ternary cases, there are at least 2 allowed gates. Can we find more? In order to find more, I will merge the 2 tables into a bigger table. And in this way, I now have this merged table is an orthogonal array with 9 rows, 4 columns, level 3, and strength 2. So rows and columns are obvious, 9 rows and 4 columns. Level 3 means there are 3 different elements, 0, 1, and 2, and strength 2. Strength is a very special property and very important to this approach. Strength 2 means that for every subarray of 9 rows and 2 columns, there is a 2 tuple in each row, and every 2 tuple appears only 1 time in this subarray. So I will explain the strength 2 in this way. So let's say we have a subarray. Okay, I just pick the first column and the third column. And this is a subarray of 9 rows and 2 columns. In this subarray, each row is a 2 tuple. Okay, each row is a 2 tuple, 0, 0, 0, 1, 0, 2, etc. And each 2 tuple appears exactly 1 time. And this feature, strength 2, exactly mimic our restrictions of non-informative. So this means that if we can insert more columns in this orthogonal array, then the newly added columns will be another new logical gates. Can we find more columns? And it happens to be fine. This is a combinatorics problem. The maximum number of the columns in such an array of n square rows, level n, and the strength 2 will be n plus 1. So this means there is an upper bound of the number of different logic gates, which is n minus 1. So this is the existence, and this is a possible upper bound. As for the existence, we know that when n is a power of prime number, then it is existed. What about the other cases? The answer is mathematically difficult. So we know the existence for the power of prime numbers. How about the construction? How do they look like? So we happen to find the construction in the case that P is a prime number. So in this case, these different logic gates can be represented in this modular arithmetic. Unfortunately, this construction is not working for prime powers. So in the following context, we will mainly focus on the prime number cases. And also later we will show the relation of this logic gates to quantum mechanics. How do they look like in linear space language? Okay, so these are the logic gates, the representations of the correlations between subsystems. And now we can deal with information. So each question has n different outcomes, and under different contexts, each question will be regarded as a collection of different outcome probabilities. The information of this question will be defined as a function of these outcome probabilities. And what's this function? This is what we mean by a weak information measure. We only restrict the upper bound and the lower bound of the information. So why not using a direct information measure? Why not using a more detailed expression? So in one hand, we are lacking or currently lacking of the intuitiveness of this measure. So perhaps we need more assumptions to restrict the form of this measure. On the other hand, this weak measure is already enough for us to derive some important consequences. And now we can formally define non-informative. So if the only knowledge we know is the interrogation of one question, and this cannot infer anything about the possible outcomes of another question, then they are pairwise non-informative. Okay, so these are the information of a single questions. And then we want to focus on the system information of the system. So previously, we assumed the subset Qn determines the state of the system. And maybe we can try taking addition of this information question in this subset. However, we miss some small issues, especially for correlation terms, because the compatible questions will introduce duplicate information. So although we haven't introduced the link between quantum questions and the quantum mechanics, but we want to first take the example to show this small issue. So this is an example of a 2-qubit system. Assume we have information of the 2 correlations, and the context will be looking like this way. So we have done 2 measurements. Under this context, the information of the sigma y tensor sigma y can be derived. So it looks like this information of sigma y tensor sigma y is not new to us. This is a kind of duplicate information. So this is a 2-dimensional case. There are only 3 mutually commuting correlations. In higher order dimensional case, there will be more collections of commuting operators, and the duplicate information becomes more and more. We actually do not want to focus on the non-derived terms. We only want to focus on the non-derived terms only. So the information of the system is indeed the sum of the informational questions in subset Qn, but have an additional restriction. So a little bit weird, partly because we are using a weak information measure. Another reason is that we want to set the upper bound of this information of the system in this way. So in an n-body system, we want to set the upper bound of the information of the system is n units. And these assumptions already help us to derive several consequences in the framework of quantum questions. These are two consequences that working on arbitrary n-array case. And later I will explain their correspondence in quantum mechanics. This is a consequence of working in prime number dimensional case only, a little bit abstract. Let's quickly go through it. Later I will recap it. This is a very reluctant assumption, I must admit. All the other consequences we will first derive in quantum question structure only, and then go back to the quantum mechanics to see whether the corresponding statement is true. For this one, I first find the correspondence in quantum mechanics and then bring it back to quantum question. Not very intuitive. It is very possible that there is a deep mathematical reason we haven't found. And this assumption helps us to yield an important consequence. So this perhaps is the most important consequence of quantum questions, the structure of the subset Qn. For a purely single system, it contains complementary questions, and the size is no more than p plus 1. This consequence determines the link between quantum questions and quantum mechanics. And now we can look at quantum mechanics to see how we establish this link. The start point will be the mutually unbiased basis, which is defined in this way. So we can see that the eigenstates of Pauli matrices are the maps in two-dimensional space. With the help of maps, we can then provide a formal definition of mutually unbiased operators. So this is the case of non-degenerate operators. It's defined based on their eigenstates. And indeed, we can see that Pauli matrices are pairwise mutually unbiased. So how about degenerate case, especially for the joint measurement, the correlation terms? We can define the mutually unbiased in the same spirit. The only different thing is that now we want to use the eigen subspace. So two degenerate operators mutually unbiased, if and only if their eigen subspace mutually unbiased. And why we introduce mutually unbiased basis and mutually unbiased operators? Because we want to find the generalization of Pauli matrices, how to generalize qubits. So in the d-dimensional space, we can always find this computational basis, okay? And based on this, we can define another set of bases in this way. This is discrete Fourier transformation, and omega will be the root of unity. So omega has the absolute value 1. These two bases, I and J tilde, will be mutually unbiased because it's obvious their inner product looks like this. Based on these two mutually unbiased bases, and then we can introduce the generalized Pauli matrices, capital X and capital Z, in this way. And when the dimension D is equal to 2, these two operators will be reduced to Pauli matrices. Where is the Y? Well, you can imagine y is equal to x multiplied z and up to a constant. Or another way we can say y is not as important as x and z. Here are some properties of generalized matrices, polymatrices. So they are cyclic with period d. And noticing that this special commutation relation is called while, named after while. Because another way to derive the generalized polymatrices is using Weil-Heisenberg group. So there is a very fruitful group structure, and perhaps we can introduce the group property to replace the non-intuitive assumption in quantum question. So here is an example of this generalized polymatrices in 5-dimensional case. Very similar to polymatrices. Okay. And there are some important effects of generalized polymatrices and mutually unbiased basis. The first is that in arbitrary d-dimensional space, there are at least 3 maps, which are the eigenstates of x, that, and xz. Or you can treat xz as a generalized sigma y. When the dimension is a prime number again, the space has a maximum number of maps, which is p plus 1. Those p plus 1 maps are the eigenstates of these operators. So each of them has this shape. This is the shape of these eigenstates, quite complex. Omega is the p's root of unity. So we can see that the prime number dimensional space is very special for both quantum mechanics and quantum question. And the correspondence is mainly built upon this prime number coincidence. And here will be the basic recipe of the link. In theory or p-dimensional case, each question with outcome 0 to p minus 1 is corresponding to an operator with eigenvalues of roots of unity. So why the eigenvalues are not real numbers? This is just for the sake of convenience, computational convenience, because we are more interested in the eigenstates of these operators, and we can always replace the root of unities into real numbers. The composite question, the logic gates, have this special correspondence. The I is ranging from 1 to p minus 1, and we think this correspondence is really non-trivial. And in this way, we can translate each of the consequences in quantum question into linear space language. For a single system, the subset of Qm just corresponds to the set of operators where eigenstates are mutually unbiased. And this is it's a relative trivial result. And because you can see that the corresponding result in quantum mechanics is a little bit obvious. For this one, I think it's a non-trivial result. This consequence, the bottom one, is deriving in I have a very rigorous proof in linear space. The top term, the consequence, is derived in quantum question structure. So both of the consequence I have a proof in 2 versions. It's very possible that this consequence have a very deep mathematical reason. For example, the group structure, but we haven't found that yet. This is the assumption, the non-intuitive assumption we used to derive the size of subset Qn. So we first prove the bottom one, the corresponding statement in quantum mechanics, and then introduce it as an assumption. And this is why we mainly focus on one body and two body systems. For every consequence we made, we derived in quantum questions. We hope there is a parallel proof in linear space language. For three body and more, the calculations in linear space become very difficult. And finally, we want to show one consequence, which is perhaps the only one on arbitrary many-body systems. It's on the agreement of degree of freedoms. For an n-body system, the subset Qn contains questions of single body, one body, two body correlations, three body correlations, and up to n body correlations. And the equation shown here is the summation of the number of these questions. So finally, we have this result. So you can see that each question, noticing that each question has p different outcomes, and it has a degree of freedom p-1 due to the normalization. And the total degree of freedom will be p to the 2n minus 1. And this is just the same as the degree of freedom of density matrix for an n-body p-dimensional quantum systems. So these are the selected consequences and their correspondences. In the very end, I'd like to show a very high-level summary of quantum questions. So we mainly focus on prime number dimensional case. First, we represent each observable as a question. Each question is then expressed as a collection of outcome probabilities, which are context-dependent. The information of a question is a function of outcome probabilities, and the information of the system will be summation of the information of selected questions. I think this framework will be covering many different informational approaches on reconstruction, including Bruckner, Zellinger, Horn, and others. And the different thing will be the basic settings of context as well as the information measure. Even though we are using a very simple way to measure information, we still obtain useful results showing the framework's great potential. And again, this work is a partial reconstruction, and we believe that by adding more specific conditions and refining the way we measure information, we could achieve a full reconstruction in the future. Okay, that's it. Thanks for the attention.
Okay, great. Questions? Yes, Philipp.
Yeah, hi, Jan. Thanks very much for this nice work. So yeah, that's very nice development. So maybe the first general question. So what stopped you from going on to do a reconstruction? Oh, we can't hear you, I believe.
Hello?
Yeah, now we can hear you, yeah.
May I repeat your question?
Oh, yeah. So first of all, very nice work. Yeah, it's very interesting. So yeah, maybe as a general question at the start, so what prevented you from going on to continue trying to push that into a full-scale reconstruction of arbitrary finite dimensional systems?
The main difficulty is the choice of the measure is on this part. For example, I have tried, for example, your measures in the two-dimensional case to the high-order case by simply replacing the 1/2 to 1/n. But unfortunately, I didn't get very further results. Another reason is I I try to combine, and I really believe there is a group structure behind the quantum mechanical side, and I want to introduce these group structures into quantum question language, but failed. So these two are the main difficulties of not going on.
Okay, maybe another question now, a bit more specifically. So these questions that you have, so generalizations of the Pauli operators, are they generators of SU, whatever dimension of the Hilbert space you're looking at? So I guess, well, SUP or something like this. We can't hear you.
Hello?
Now we can. Yes.
Okay. In two-dimensional case, it's a U2, and for the odd number cases, it's SUN. Yeah.
Okay, so they are generators of these groups. Okay. Then here, when it comes to the total amount of information that you associate with the system, this went a little bit fast. Am I correct that you try to only pick out basically, yeah, here I think when you say QI, I guess, what does it mean, relative independent or something? So basically for 2 qubits, you would want to pick out only, let's say, 2 questions when you're answering 2, so that the total information is only 2 for a pure state in that case. But then doesn't that become a little bit cumbersome because that becomes very context dependent, which questions you pick out and which not? So why not pick, do the total information about all the questions that sit inside a full basis of your full basis of questions, so a full maximally informationally complete set of questions. Why not that? So it turned out to be very convenient in the reconstruction for qubits.
Yeah, the one problem is that I currently haven't got a proof that the complete these set of complete maximal complete questions in arbitrary higher dimensions, and currently only focus on the, as you mentioned, is on the pure states, and the specific we actually mainly focus on the maximal entangled state because our information measure is very weak. So as long as we're only dealing with the maximal entangled states case, and then we can define we can only pick up the independent terms compared to the context.
Yeah.
Because our condition is very restricted.
Hear you again, sorry.
Sorry. Hello.
Can you say again what you were just saying? Yes.
Sorry for the inconvenience. Because our information measure is very weak, so we mainly focus on the maximal entangled state. In this special case, the questions that are independent on the context can be easily picked up. So we just choose this way.
Okay.
I agree with what you say, but I haven't got a full proof on arbitrary p-dimensional case.
I see. Then maybe one, or am I allowed to ask another question? On the definition of the question sets for composite systems, it seemed to me like you were only restricting to logical connectives between, one question from one subsystem and one question from the other subsystem. But you can also have logical connectives of composite questions in general. So are you disallowing them here? Please wait 5 seconds. I think no.
Okay. As for this one, because this is just a on my original motivation is that the logic gates will be a mimic of a tensor product. So in binary cases, indeed, there's a tensor product. So we didn't consider the further connecting case.
I see. Yeah, it's for the reconstruction actually interesting to also allow the other ones, because then it turns out for quantum mechanics, it's actually such that the higher composites turn out to be, at least for, let's say, 2 qubits or so, to be determinable in terms of just bipartite questions. But that's a non-trivial output in the end. It's not an input.
Yes, I understand your meaning. I have a similar. I have
seconds always before answering.
I see. What you said, the similar consequences in quantum mechanics is true. For example, I can show you a consequence. Mm-hmm. For example, maybe this one. So for example, these p+1 mutually commutative cases, their eigenstates will be maximal entangled states. So for example, if for any two of them has eigenvalue omega, say omega m and omega m, the other p-1 eigenvalues will have this relation, and star I m. So this is a similar feature as what you said. However, I didn't carry out this feature in this generalization. One main question is I cannot reduce the cyclic terms into the simple correlation terms.
I see. Yeah. I mean, it's indeed quite intricate and much more complicated than the qubit case. So yeah, thanks for looking into this. I look forward to a paper or so that will hopefully come out at some point. Very interesting. Thanks very much.
So thank you very much, Yang Yu. Great. Let's thank the speaker.